Section: Introduction. In this section, we explore how humans often take time to think through difficult problems to enhance their decision-making. We ask whether we can give large language models, LLMs, a similar ability. Specifically, we want to know if we can help these models use extra computation during testing to improve their answers. The idea is that with more computation, an LLM could perform better than it did during training. This capability could also open new possibilities for tasks that require reasoning and agency. For example, if we can trade off the size of a pre-trained model for more computation during inference, we could use smaller models on devices instead of relying on large models in data centers. Automating the generation of better outputs through additional computation could lead to a self-improvement algorithm that needs less human input. Previous research on using computation at test time has shown mixed results. Some studies indicate that LLMs can enhance their outputs with extra computation, while others suggest that their effectiveness is limited for complex tasks like math reasoning. This inconsistency highlights the need for a thorough analysis of different methods for increasing test time computation. We are particularly interested in the advantages of scaling up this computation. One of the simplest and most researched methods is best-of-n sampling, where we generate multiple outputs from a base LLM and choose the best one based on a learned verifier or reward model. However, there are other ways to utilize test time computation. By changing how we gather responses or how we use the verifier, we can significantly improve the effectiveness of test time computation, as we demonstrate in our paper. To investigate the benefits of scaling test time computation, we conduct experiments on the challenging math benchmark using PaLM-2 models. These models are fine-tuned to either correct wrong answers or verify the correctness of steps in an answer. We find that the success of a test time computation strategy depends on the specific problem and the base LLM used. For easier problems, allowing the model to refine its initial answer through a series of revisions may be more effective than generating multiple independent responses. Conversely, for more difficult problems that require exploring various approaches, generating new responses in parallel or using a tree search method with a reward model may be more beneficial. This leads us to propose an adaptive, compute-optimal strategy, where the method for using test time computation is chosen based on the prompt to maximize the benefits of additional computation. We also show that we can predict the effectiveness of test time computation based on the difficulty of the question, allowing us to implement this strategy practically. By allocating test time computation wisely, we significantly enhance our scaling approach, outperforming a best-of-n baseline while using about 4 times less computation. We then investigate how much test time computation can replace additional pre-training. We compare a smaller model with extra test time computation to a much larger model that has been pre-trained. We find that for easy and intermediate questions, and even some hard ones, using additional test time computation is often more effective than simply scaling up pre-training. However, for the most challenging questions, we see little benefit from increasing test time computation. Instead, we find that additional pre-training is more effective for these cases, indicating that scaling test time computation and pre-training may not be directly interchangeable. Overall, our findings suggest that even with a basic approach, increasing test time computation can be more advantageous than just focusing on pre-training, with potential for further improvements as our strategies develop. In the long run, this points to a future where we spend fewer resources on pre-training and more on inference. Section Summary. In this section, we explore how to enhance large language models, LLMs, by utilizing additional computation at test time to improve decision-making and accuracy, particularly for complex tasks. We find that the effectiveness of test time computation strategies varies based on problem difficulty and the base LLM, suggesting that an adaptive approach to scaling test time compute can outperform traditional methods while potentially reducing the need for extensive pre-training. Section: A Unified Perspective on Test Time Computation, Proposer and Verifier. In this section, we unify various approaches to test time computation and analyze some key methods. We begin by considering how additional computation at test time can adaptively change the model's predicted distribution based on a given prompt. Our goal is to enhance the outputs beyond what we would get by simply sampling from the language model. We identify two main ways to adjust the model's distribution. First, by modifying the input prompt with extra tokens that the model uses to refine its predictions. Second, by sampling multiple outputs from the model and then refining these outputs. Essentially, we can either improve the model's initial predictions or use additional verification methods to enhance the final outputs. This process is similar to Markov chain Monte Carlo sampling, where we combine a simple proposal distribution with a scoring function. To improve the proposal distribution, we can optimize the model for specific reasoning tasks using reinforcement learning-inspired fine-tuning methods. These methods do not require extra input tokens but focus on enhancing the model's ability to generate better outputs. Additionally, techniques like self-critique allow the model to iteratively assess and improve its own outputs during test time. We fine-tune models to revise their answers effectively in complex reasoning scenarios by using on-policy data and guided improvements. Regarding the verifier, we use it to select the best answer from the proposal distribution. A common method is best-of-n sampling, where we generate multiple solutions and choose the best one based on the verifier's assessment. We can enhance this by training a process-based verifier that evaluates the correctness of each step in a solution, allowing for a more efficient search through potential answers. Next, we explore how to optimally scale test time computation to enhance model performance for a given prompt. We aim to determine the best way to allocate our test time compute budget. For instance, when using a revision model as the proposal distribution, we can either generate multiple independent samples at once or create a sequence of revisions and select the best one. We expect that simpler problems may benefit more from revisions, while more complex problems might require exploring various strategies through independent sampling. We also have different search algorithms to choose from when using verifiers, each with unique advantages depending on the problem's difficulty. More advanced search methods may be more beneficial for challenging problems compared to simpler approaches. Ultimately, we want to identify the best allocation of our test time compute budget for any given problem. We define the test time compute optimal scaling strategy as the approach that selects hyperparameters to maximize performance for a specific prompt. We aim to find the hyperparameters that yield the highest accuracy for the model's output based on the given compute budget. Section Summary. In this section, we unify various test time computation methods for language models, focusing on how to adaptively modify the model's predicted distribution through input and output adjustments to improve performance. We also explore optimal strategies for allocating test time compute budgets, balancing between generating multiple independent samples and refining outputs to maximize accuracy for specific prompts. Section: Estimating question difficulty for compute optimal scaling. In this section, we estimate the difficulty of questions to analyze the test time scaling properties of various mechanisms, such as the proposal distribution and the verifier. We approximate the optimal strategy based on a statistic that reflects the difficulty of a given prompt. This compute optimal strategy is linked to the prompt's difficulty, and although it is an approximation, it significantly improves performance compared to a random or uniform allocation of compute resources. We categorize each question into one of 5 difficulty levels, which allows us to estimate the optimal strategy for a specific compute budget on a validation set. We then apply these strategies to the test set, selecting the best compute strategy for each difficulty level independently. This means that question difficulty serves as a key factor in designing our compute optimal strategy. To define question difficulty, we follow a method that uses the model's pass rate on test questions, based on 2048 samples, and divide this into 5 quantiles representing increasing difficulty. We found that these model-specific difficulty levels are better predictors of effective test time compute usage than the manually labeled difficulty levels in the math dataset. However, we acknowledge that determining a question's difficulty in this way assumes we have access to a perfect correctness checking function, which we do not have in practice. To make our approach feasible, we first estimate difficulty using a model-predicted method, which involves binning the average scores from a learned verifier instead of relying on ground truth answers. We call this model predicted difficulty, contrasting it with oracle difficulty that depends on knowing the correct answers. While model predicted difficulty avoids needing the true labels, it does add some computational cost during inference. However, this cost can be integrated into the overall computation when running the inference strategy. This situation resembles the exploration-exploitation trade-off in reinforcement learning, where we must balance the compute used for assessing difficulty against applying the best compute strategy. This is an important area for future research, and for simplicity, our experiments do not account for this cost, focusing instead on demonstrating the potential of effective test time compute allocation. To prevent bias from using the same test set for both computing difficulty bins and selecting the optimal strategy, we employ twofold cross-validation. We determine the best performing strategy based on one fold and then evaluate its performance on the other fold, averaging the results. In our experimental setup, we analyze various verifier designs and proposal distributions, starting with the math benchmark, which includes high school-level math problems of varying difficulty. We use a dataset split of 12,000 training questions and 500 test questions. Our analysis utilizes the POM2S Cody base model, which we believe reflects the capabilities of many modern language models. This model performs well on math and has not yet reached its performance limit, making it a suitable choice for our tests. Finally, we explore how to scale test time compute by optimizing a verifier, examining different methods for conducting test time searches with process verifiers and analyzing their scaling properties. Section Summary. In this section, we estimate question difficulty to optimize test time compute strategies by categorizing prompts into 5 difficulty levels based on a model's performance, allowing us to select the best compute strategy for each level. We utilize a model-predicted difficulty approach to avoid needing ground truth answers, balancing the computation cost of assessing difficulty with the application of optimal strategies, while conducting our experiments on the math benchmark using the POM2S model. Section: Training verifiers amenable to search. In this section, we discuss our approach to training verifiers that are suitable for search tasks. Initially, we used the PRM training method, which relied on labels from human crowd workers. However, when we examined the PRM 800K dataset they released, we found it to be ineffective for our needs. We discovered that a PRM trained on this dataset could be easily manipulated using simple strategies like best-of-n sampling. We believe this issue arises from a difference in the data distribution between the samples generated by GPT-4 in their dataset and our POM2 models. Instead of going through the costly process of gathering human labels for our models, we opted to supervise the PRMs without them. We did this by estimating the correctness of each step through Monte Carlo rollouts during the solution process. Our PRM's predictions at each step represent value estimates for the expected rewards of the base model sampling policy, similar to recent studies. We also compared our results to an ORM baseline but found that our PRM consistently performed better. Therefore, all search experiments in this section utilize a PRM model, with more details available in the appendix. For answer aggregation during testing, we can use process-based verifiers to score each step in a set of solutions generated by the base model. To choose the best answer from a set of n options using the PRM, we need a method to combine the per-step scores for each answer. We first aggregate the per-step scores for each individual answer to get a final score, and then we aggregate these scores across all answers to find the best one. In terms of stepwise aggregation, instead of using methods like taking the product or minimum of the scores, we found that using the PRM's prediction at the last step as the score for the entire answer yielded the best results. For inter-answer aggregation, we apply a best-of-n weighted selection method, which considers the verifier's correctness scores across all solutions with the same final answer, choosing the one with the highest total score. We optimize the PRM during testing using various search methods. We explore 3 approaches that sample outputs from a few shot prompted base LLM. One method is best of n weighted selection, where we independently sample n answers and select the best based on the PRM's judgment. Another method is beam search, which enhances the PRM by examining its per-step predictions. We maintain a fixed number of beams and a beam width, sampling initial predictions, scoring them, filtering for the highest scores, and then sampling proposals for the next step, repeating this process until we reach the end of a solution or a set number of rounds. Lastly, we introduce look-ahead search, which alters how beam search evaluates steps. Instead of relying solely on the PRM score at the current step, look-ahead search simulates future steps to improve value estimation. We perform rollouts up to a certain number of steps ahead, using the PRM's prediction at the end of the rollout to score the current step. This method can be seen as a specific case of MCTS, where we remove stochastic elements since our PRM is already trained and fixed. This approach allows us to focus on exploiting learned values rather than exploring new ones, making look-ahead search a practical application of MCTS-style methods during testing. Section Summary. In this section, we describe our approach to training a PRM without human labels by using Monte Carlo rollouts for per-step correctness estimates, which outperforms an ORM baseline. We also detail our search methods, including best of n weighted selection, beam search, and look-ahead search, to optimize the PRM's performance in selecting the best answers from sampled solutions. Section: Analysis Results. Test time scaling for search with verifiers. In this section, we present our findings on various search algorithms and identify a compute optimal scaling strategy for these methods based on the difficulty of prompts. We begin by comparing different search settings, focusing on the standard best of n approach and 2 key parameters that differentiate tree search methods: beam width and the number of look-ahead steps. Although we cannot explore every possible configuration, we examine several settings within a maximum budget of 256. These include beam search with a beam width equal to the square root of the generation budget, a fixed beam width of 4, and look-ahead search with different values of look-ahead steps applied to the beam search settings. To ensure a fair comparison of search methods based on the generation budget, we establish a protocol to estimate the cost of each method. We define a generation as a sampled answer from the base language model. For beam search and best of n, the generation budget corresponds to the number of beams and the number of samples, respectively. Look-ahead search, however, requires more computation since it samples additional steps ahead, leading us to define its cost as the number of samples multiplied by 1 more than the number of look-ahead steps. Our results indicate that with smaller generation budgets, beam search outperforms best of n significantly. However, as the budget increases, the advantages of beam search diminish, and it often performs worse than best of n. We also observe that look-ahead search generally underperforms compared to other methods at the same budget, likely due to the extra computation involved in simulating look-ahead rollouts. This decline in performance may stem from the model generating repetitive and low information steps towards the end of a solution. In some cases, overly optimizing search leads to very short solutions, which explains why look-ahead search, the most powerful method, tends to underperform. To understand which problems benefit from search, we conduct a difficulty bin analysis, comparing beam search with a beam width of 4 against best of n. Our findings show that while both methods perform similarly at high generation budgets, their effectiveness varies across difficulty levels. On easier questions, beam search's performance declines as the budget increases, indicating exploitation of the model's predictions. Conversely, on harder questions, beam search consistently outperforms best of n, and on the most difficult questions, neither method shows significant progress. These results suggest that question difficulty is a valuable indicator for predicting the optimal search strategy at a given compute budget. We visualize the compute optimal scaling trend, showing that in low-budget scenarios, using both Oracle and predicted difficulty, we can achieve performance close to best of n while using significantly less compute. In higher budget scenarios, the benefits of predicted difficulty diminish, but we still see improvements with Oracle bins, highlighting the advantages of adaptively allocating compute during search. Next, we shift our focus to refining the proposal distribution. We explore how modifying the proposal distribution can enhance performance. We allow the model to iteratively revise its answers, aiming to improve its distribution at test time. Simply prompting existing models to correct their mistakes is often ineffective for reasoning problems. Therefore, we build on established methods, adapt them for our context, and fine-tune language models to revise their answers iteratively. We will describe our training process and analyze the inference time scaling properties of these revision models. Section Summary. In this section, we present our analysis of various search algorithms, revealing that beam search outperforms best of n with smaller generation budgets but underperforms as budgets increase, particularly on easier questions. We also identify that the optimal search strategy varies with question difficulty, allowing for significant compute savings by adaptively scaling test time compute based on this difficulty. Section: Setup, Training and Using Revision Models. In this section, we outline our approach for fine-tuning revision models, which shares similarities with existing methods but includes key differences. For fine-tuning, we require sequences of incorrect answers followed by a correct answer, allowing us to apply supervised fine-tuning. Our goal is to ensure that the correct answer relates to the incorrect ones, helping the model learn to identify and correct mistakes rather than starting over. To generate revision data, we found that the on-policy method for obtaining multiple responses was effective but not practical due to high computational costs. Instead, we sampled 64 responses simultaneously at a higher temperature and then created multi-turn rollouts from these samples. We paired each correct answer with a set of incorrect answers to form our training data, including up to 4 incorrect answers, with the number chosen randomly. We used a character edit distance metric to select incorrect answers that were related to the correct answer, which helped us train a meaningful revision model. During inference, we can sample a sequence of revisions from our fine-tuned model. Although the model was trained with a maximum of 4 previous answers, we can extend this by only keeping the most recent 4 responses. Our results show that as we sample longer chains, the model's accuracy improves, indicating it learns from past mistakes. However, we noticed a shift in distribution at test time, where correct answers in the context could be mistakenly revised to incorrect ones. We found that about 38% of correct answers were turned incorrect using a basic approach, so we implemented a selection mechanism based on majority voting to choose the best answer from the revisions. To evaluate the effectiveness of our revision approach, we compared the performance of sequential revisions against parallel attempts at answering questions. Our findings indicate that sequential sampling, using both verifier-based and majority-based selection, outperforms parallel sampling. We also explored how sequential and parallel sampling might have different advantages. Parallel sampling can cover a wider range of solutions, while sequential sampling refines existing answers. We propose a balanced approach, allocating some resources to parallel sampling and the rest to sequential revisions. Our analysis shows that there is an optimal ratio of sequential to parallel sampling that maximizes accuracy, which varies based on the difficulty of the questions. By determining the ideal ratio for different difficulty levels, we can significantly enhance test time efficiency. Our results demonstrate that using this compute optimal strategy can lead to substantial improvements, allowing us to achieve better performance with less computational effort. Overall, we highlight the potential for optimizing test time compute by refining the proposal distribution based on the specific prompt. Section Summary. In this section, we describe our approach to fine-tuning revision models using sequences of incorrect and correct answers to enhance the model's ability to identify and correct mistakes. We find that a balanced allocation of sequential and parallel sampling during inference improves accuracy, particularly by adapting the strategy based on the difficulty of the questions, ultimately achieving better performance with reduced computational costs. Section: Putting it together, exchanging pre-training and test time compute. In this section, we explore how additional computation during testing can enhance our ability to represent complex distributions, which can lead to better performance. We suggest that this flexibility allows us to compensate for not having a more powerful model or for not using more computational resources during pre-training. We aim to understand the extent of this possibility by asking whether we should focus on increasing pre-training computation or on adding more computation during testing. When we increase the computational resources for pre-training, we face a choice. Should we use that power to train with more data or to increase the model's parameters? We concentrate on the scenario where we scale up the model parameters while keeping the amount of training data constant, similar to the approach used in the llama models. This choice reflects a common method for scaling pre-training resources, and we will leave the analysis of a more balanced scaling of data and parameters for future research. Next, we define how to exchange pre-training and inference computation. For pre-training, we can estimate the computational cost using a formula that involves the number of model parameters and the number of tokens used for training. For inference, we use a similar formula based on the number of tokens generated during inference. If we increase the model parameters by a certain factor, both pre-training and inference costs will also increase by that factor. To align the computational costs of a smaller model with those of a larger one, we can adjust the inference computation based on the ratio of pre-training to inference tokens. This ratio, which we call R, can vary significantly depending on the specific application. In many large-scale settings, we might have many more inference tokens than pre-training tokens, leading to a high R value. Conversely, in self-improvement scenarios where we generate fewer inference tokens, R would be low. Thus, the amount of computation we can apply during testing is influenced by this ratio, and we anticipate different outcomes based on the context. In our analysis, we compare our compute optimal scaling against a scenario where we increase model parameters significantly. We examine 3 different values of R, which correspond to different inference budgets. Our findings suggest that if we expect to encounter challenging questions or have a larger number of inference tokens, it is often more beneficial to invest in pre-training. However, if we anticipate mostly easier questions or have lower inference needs, utilizing test time computation proves to be more effective. In our discussion, we highlight that our analysis shows a strong link between the effectiveness of various techniques and the difficulty of the problems faced by the base model. We introduce the concept of compute optimal scaling, which adapts our strategy based on the specific prompt and available computation. By implementing this strategy, we can enhance the efficiency of test time computation scaling significantly. We also recognize limitations in our study and suggest areas for future research. We focused on 2 main mechanisms for improving test time computation: the verifier and the proposal distribution. However, we did not explore combining these with other techniques, such as critique and revise. Future work should investigate how to enhance test time computation by integrating various approaches. Additionally, we used question difficulty as a simple measure to guide our scaling strategy, but estimating this difficulty requires considerable computation. Future research should seek more efficient methods for assessing question difficulty, possibly through pre-training or fine-tuning models to predict it directly. Lastly, while we concentrated on test time computation, we envision a future where the results from additional testing can be used to improve the base model itself, creating a cycle of self-improvement. Future studies should explore how to leverage the outputs from test time computation to enhance the underlying model. Section Summary. In this section, we explore the trade-off between pre-training and test time compute, proposing that additional test time computation can compensate for the limitations of a lower capacity model. We analyze how the ratio of pre-training to inference tokens influences the effectiveness of this exchange, finding that in certain scenarios, leveraging test time compute can yield better performance than increasing pre-training compute. Section: Acknowledgements. In this section, we express our gratitude to Yi Su, Rishabh Agarwal, Yin-Lam Chow, Alexandra Faust, Vincent Zhuang, George Tucker, Hao Lu, Jai Pan, Ethan Dyer, Behnam Neshabur, Xavier Garcia, Yamini Bansal, Lampros Lampro, Yushao Ku, and Amrith Settler for their valuable feedback on an earlier version of our paper and for engaging discussions. We also thank Rishabh Agarwal, Vincent Zhuang, Yi Su, and Avi Singh for their insightful ideas and experiments that clearly showed the potential of generating pairwise samples for training revision models, as well as for sampling based on edit distance. Additionally, we appreciate Slav Petrov for his leadership support.